We have all founders and very deep technical founders on the stage. So we're going to skip intros and get right into it. I think today, a lot of the blockchain industry has really been focused on low throughput chains. You guys have each taken the stance that chains ultimately will be high throughput, so I'd love to start the conversation there.
Absolutely, so I can start off. I mean, I think in the context of Ethereum, like it's not that it's a theoretical thing. I think it's a pragmatic thing of like, why is low throughput not working? Like you look at, you look at Ethereum today, you see 12-second block times, processing about 1 million transactions a day, costing around $12 a transaction or something like that. And so there are some things you can do with that. There's a lot of things you can do with that, actually. But it turns out like most of those things are high-value DeFi. And so if you want more use cases, like you're going to need to have more throughput because that lets you have lower fees because you're not letting folks box out. You want to have lower latency because that opens up the use cases that you can do. And so I think like, you know, I think there's going to be broad agreement on this panel, but like that's the thesis for why you need more throughput than we have in the EVM land today.
And Keone, I think the Monad team has been explicitly opinionated that the EVM landscape needs higher throughput, kind of going from kilobytes ultimately to megabytes and beyond. What's your take on that?
Yeah, I think at the end of the day, Ethereum has proven out the incredible value of shared global state and the incredible value of a world computer where anyone can run a node, anyone can verify the state of any transaction. But I think when it comes to pragmatism, like if you're a small business owner and you're trying to accept payments using crypto rails, you want to be able to run a full node to be able to actually verify that when someone sent you a transaction that sent money, you can let the person walk out of the store or drive off of the Tesla lot or whatever it is, and be sure that there was no double spend per se. And in order to really facilitate that story and have crypto be this means of settlement, we just need to scale to much higher throughput. But the good news is that we're currently starting from a baseline that is very conservative, and there are opportunities coming from introducing asynchronous execution to utilize much more of the block time for execution, or introducing parallelism for transaction execution, or improving the state access substantially in order to take that same standard and then scale it to a much higher throughput landscape.
And Avery, the Aptos team and also with Monad have kind of made the explicit decision to do block STM, a different form of parallelism than what Sui and Solana are doing. I would love for you to kick off the conversation about why block STM.
I'd love to do that, thanks. So when we think about the history of execution in the blockchain space, you have sequential with Ethereum, as we kind of started off with, just single process, doing transactions one at a time. We have the static parallel execution where we kind of declare dependencies up front, and then we have things like Sui and Solana with taking that path. And then we think about Aptos, which is dynamic parallelism. It is the idea that we can take information at runtime and optimize for the most concurrency possible, and also drive as much concurrency as possible in that shared state through things like aggregators and others. And that was kind of the general concept of how block STM works. So having a dynamic kind of runtime parallelism that can take as much information for scheduling as best as possible unlocks the most concurrency that you can have. I'll give you an example of that. Say you have a centralized order limit book organized as a tree of nodes and a way for you to kind of put orders in that tree. You don't have to lock that whole tree when you don't know exactly what pieces you're gonna access. Dynamic parallelism allows you to kind of go access different nodes of that tree and extract the most concurrency possible, removing false sharing and making sure that you can run as many transactions as you can.
And Sam, I'm sure you have some opinions as well, because I think with generally all the high throughput blockchains, what they've all also been opinionated on is doing parallel processing and the different flavors of parallel processing. Sui is doing a little bit more state access lists. Can you talk about why Sui made that choice?
Yeah, absolutely. So we do something that's a little bit different than state access lists. We have an object-centric data model where a transaction specifies, okay, here's the move functions I'd like to call, and here's the objects I'm going to pass to those functions. And then this information makes it easy for the runtime to figure out what transaction is going to touch which object, and then allocate efficiently, okay, if all these transactions are touching the same object, they'll go to this thread. If this transaction is touching a different object, we'll allocate it to different threads, and so on and so forth. So this is an effective scheduling strategy. Dynamic is also an effective scaling strategy. I think like both of these things can work. I think where having static dependency information or object information like really starts to help is in two areas. So one is in local fee markets. So of course, like we all love parallel execution, and parallel execution works well, but it works well when somebody hands you a workload that has nice parallelism in it. If they don't, if they hand you a purely sequential workload, then like you're no better than your old school chain that has just one thread. And a superpower we have in crypto is that we have some control over what workload we get because we can set up an incentive feedback loop. And so basically, like, this is where I think the static dependency information really shines, because you can say, if there's a bunch of transactions that want to touch the same object and that object is hot, you can make the fees go up for that, whereas the fees for other things go down. And then this also means that you don't end up scheduling too many transactions that are touching the same object, and then the fast transactions have to wait for the slow ones. I think the other area where this matters is if you want to do horizontal scalability. So this story we told about you want to schedule execution across multiple threads. Now maybe I want to do it across multiple machines. And so there, the cost of a misprediction, say if you're using dynamic techniques, is a lot higher. Like you think this is going to touch a certain object or account, you send it to a remote machine, it turns out it actually is going to touch an account on a different machine, then things get trickier. Whereas with Sweeb, our research team has worked on, or the Mysten Labs research team has worked on this pilot fish prototype where they show we can scale execution not only across cores, but across nodes and without sacrificing latency. And this is possible because you have this upfront information about what a transaction is going to touch, and that lets you efficiently allocate transactions to the data they need to touch, and you don't get surprised by mispredictions.
Just to mention one quick thing about the sort of like feasibility of local fee markets in the context of static dependencies versus dynamic. It's still possible to have local fee markets with dynamic. Like it's just more like after the fact you go and adjust, give a rebate, like maybe overcharge a little bit initially, and then give a rebate based on what the actual state access patterns were.
So I think this helps the fee issue, but what about with the efficient scheduling issue? Like say you've already made the decision to touch a bunch of transactions that are touching the same piece of state. It's too late to go back and undo that decision, so you can rebate the folks who aren't touching that hot state, but how do you deal with that?
Yeah, I think one thing to point out is that at the end of the day, the cost of contention is, it's a little bit unclear. Like it is true that if you have a bunch of transactions that have serial dependencies, ultimately the execution, like the real execution of those transactions has to be serial. But I think the reality is that the biggest cost for execution is actually state access. So at least in monads, dynamic parallel execution, or what we refer to as optimistic parallel execution, you could think of it as a two-phase approach where the first phase is executing a bunch of transactions in parallel, assuming that they're starting from the same starting point. But then when the commitment is done, commitments are all done on those pending results in serial order. And re-execution is usually quite cheap because those state dependencies are in cache.
Right.
So I think that, at the end of the day, it is really, like there are trade-offs. There is actually a benefit to accessing state that's hot. It's not all about like contention, like reuse of state is a bad thing.
Yeah.
No, Avery, I know you have some opinions on this as well.
Yeah, definitely. So I think good points by both folks here, but I'll kind of say you don't need to trade off between the two, because the way we're thinking about dynamic parallelism is that, yes, we can optimize at runtime, which is really great for concurrency. The other thing great about it is that programmers don't need to actually specify their dependencies up front and kind of limit the scope of what the transaction can do. But the second thing is that we also want to enable hints, so that if they do want to specify those dependencies up front, they can do that. And so you can end up with this great world where programmers can kind of decide the path they want to pick in and choose. And then, when it comes down to the scaling aspect, it's not an issue as long as most of those transactions can be known up front and then scaled out and parallelized. But the other aspect I would say is, when it comes to the decision here, it's not really an if or other choice. It's the ability to take these runtime decisions and then make a decision as best as possible. So we take the low fee market, for example. You can even do that in dynamic world, right? So as you see those transactions piling up for shared hot state, you can then decide at runtime, I want to slow down the access to those transactions while leaving all the other lanes free for you to kind of continue on. And so, while pilot phase is very interesting, theoretically, I think the results we saw for them were like, 60K TPS or so. You can do that on a single machine. So what I'm saying is, and we've run experiments here, like trying out some of these different strategies. So what we've seen also is that the horizontal scalability of a dynamic parallel system is actually applicable to millions of transactions per second. We'll actually have a paper kind of coming out later describing this, in Q4 describing how it's possible to kind of get that horizontal scaling to a large level. But I think the takeaway I want to have is, it's not an if or other choice. You can actually have both, and that's what we kind of think of when we think of dynamic parallelism in Aptos.
Yeah, I totally agree with you on that, to be fair. Like, I think the static information versus dynamic information, you can have both. And like, it's always better to have more static information. It gives you more, more choices. You can always ignore it if it's not helpful or if you don't want to. So I think these hybrid approaches are going to be the right long-term way. I understand Monad is sort of doing something hybrid with some static analysis and some block STM or the dynamic approach as well.
Yeah, correct. The workload is really scheduled in an optimistic fashion. I think with respect to static analysis, that's more static analysis for state access, state dependencies, but purely within the black box of execution.
Cool. No, I think this is interesting because each of both Monad and Aptos have taken the block STM approach. Sui and Solana have taken the more deterministic approach. And comparing and contrasting these each, I think one of the other interesting things as we start to continue to explore high-performance blockchains and really continuing to get the most performance out of them is really around how many leaders should we have? Should we have 1 leader, 2 leaders, 10 leaders? Would love to open that up to the panel.
Well, I think as many as you have validators. Like, more leaders is better, right? Like, more folks to submit transactions to, more folks to blend into the block. Now, like, getting this to work is tricky, of course, but like, that's what these DAG-based consensus protocols like Mysten have been working on. I think classically, this has been a throughput latency trade-off. You get better throughput because you have more folks in the protocol that can make progress at the same time. But you get higher latency because it takes longer to actually reconcile those DAG views and to commit them. With Mysten, I think it's fair to say like that trade-off no longer exists. Like the message delay is the same as classical single leader BFT, like the 3 message delays. And so we get this very, very low latency, like 700 milliseconds end to end, a little bit faster or slower depending on where in the world you are. We're to the point where like that matters as much as anything else. But I think a lot of other folks are going to go in this direction just because like there are clear benefits, and it's just like the design of these protocols is very subtle. So it's taken a long time to get it right and to get the engineering right as well.
And there's kind of been some conversations even with the Ethereum community, the Make Ethereum Great Again community, to go multi-leader.
I'm happy to jump in next. So I think single leader versus DAGs, it's a great discussion point, but it's kind of not the key point, I'd say. It's more about, talking earlier about asynchronous execution. It's about separating the data dissemination from the actual consensus piece, because the data dissemination of transactions is really expensive. That's a lot of data flowing throughout the network. The agreement on it can be very quick. It's a very small amount of data being passed across a small number of validators. And so, with our Jolteon++ protocol, we've been super excited about kind of matching this quorum store, which is data dissemination, with a super fast, like super reliable, leader-based reputation like a BFT consensus. And it works really well, about the same as latencies as Sui's Mysten. But I think one of the biggest trade-offs with Mysten that we've seen is that it uses an uncertified DAG. An uncertified DAG is different than kind of a certified DAG. And so, when you certify DAG, you have this situation where some of these kind of nodes, if they perform badly, if they're unavailable, they kind of block the progress of things. And so while we kind of looked at the DAG research with Shoal++ and Shoal and others, it's something that we're trying to make sure we find a balance of having limits on how bad things can go. If some nodes go bad, that's why the leader reputation is important. That's why handling the certified DAG is important. But definitely the 3 ops of latency and the kind of theoretical optimal latency is really, really important for all consensus protocols.
Any opinions, Keone?
Well, I would just emphasize that from the very start, the design of Monad has been to preserve EVM compatibility and preserve Ethereum compatibility from just entirely like the shape of the blockchain. You'd think of it as a puzzle piece with the same shape that the Ethereum puzzle piece has, so that all other puzzle pieces, when interacting, have the same kind of interaction. And so that's motivated a lot of the decisions, both with respect to not having access lists, for example, just to go back to where we were before, because the reality is that most wallets don't support access lists. There's a huge adoption curve so even if we thought that it was the right approach to do that, which we don't, for various other reasons. The reality is that the most important thing is to preserve support for Ethereum so that all the same tooling that developers are used to, whether that's Foundry or the Graph or Alchemy, other things like that, all just work out of the box. And I think from the perspective of, Ethereum also is a single leader mechanism. And I think that has, similar implications there to preserve full compatibility for all tooling and infrastructure.
And both Sam and Avery, you guys and the respective teams have spent a lot of time on DAG architectures. Avery, you mentioned really the key thing, separating data dissemination from consensus. Maybe we can nerd out on those designs a little bit more, because I think they're pretty integral in kind of how you guys have built the blockchain.
I mean, I think of that one, there's more agreement than there is disagreement. Like, I haven't heard as much about the Raptor and this next generation of protocols, but it sounds like it's going in a similar direction. I think we're in the advantages. There are these certain details of the edge cases and consensus are always the hard parts. We're certainly looking at a lot of extensions along those lines as well. Yeah. But I don't think it's static versus dynamic information where we could probably go into 5 more rabbit holes.
I mean, I'd be happy to talk about Raptor for a couple minutes, if that's okay, since you bring it up. I mean, I think we're, like I said, with Jolteon++, we've already got amazing latencies in place, but with Raptor, we're excited about kind of even pushing that further down, because the idea is that as we can start to bundle, right now we have a very pipeline architecture, which we think has been, asynchronous is to some degree that, but we think pipeline is even better because you can separate all the stages and think about how a modern day superscalar CPU can kind of optimize for very high throughput and very good latency. But Raptor will allow us to kind of compress these stages together and get the blockchain latency to be the same as consensus, which is really the theoretical best you can do. Today's consensus theoretical best, but you want the blockchain to be theoretically best as possible as well. So we're pretty excited about that, and then solving that kind of the edge cases you mentioned, the uncertified DAG issue where a single node can kind of block and increase latency by 10x is a really bad outcome. We've got to make sure we solve those problems, and Raptor is a really good first step in that direction.
Cool. I guess one Mysten difference that could be worth mentioning is, Sui has had this fast path from the beginning where we do full consensus for transactions that require full agreement, and then we have this fast path for payments, for NFT minting, for publishing, just for a lot of these things where you can do things faster. And so there, 700 milliseconds is quite good. We get 400 milliseconds on the fast path, which is even quicker. And so the initial release of Mysten is just the consensus, but there's a new implementation of the fast path, and the way it integrates into Mysten reduces a lot of the overhead of signature checking, and also enables some new features at the programmability level, like being able to look up the public keys that are signing. So that's something that we think will be coming in the fall that we're also super excited about, the Mysten FP. And then also it just simplifies the protocol quite a bit, because originally we had FastPath and we had Narwhal, and we sort of tried to make them fit together, whereas Mysten was designed to end-to-end to have these 2 core parts just fit together really, really nicely.
I think kind of the broader maybe context of all these designs is, as you kind of hit some of the limitations of the blockchain, you can increase the bandwidth to all the nodes so that you can have more throughput. As you enable parallel processing, you can go from 1 core, 2 cores, 4 cores. Is there any limitations to that? Perhaps you do different types of sharding within the industry, whether that's intra-validator sharding, kind of having one node be multiple hardware devices act as one node, or I think I got those backwards, intra-validator sharding, where it's multiple hardware act as one, or you just have explicit machines where that's more opaque to users.
Yeah, I mean, on that, intra-RA sharding, validator sharding is the approach we take, and what we've done with Pilotfish, just because when you have the sharding details inside the black box of what the validator is, you just have a lot more design flexibility with what you can do. You don't need BFT assumptions between those nodes. They're all run by the same operator. They can be in the same data center, and you can just use way more classical Web 2 techniques. That's what we do with Pilotfish is very much inspired by stuff that folks have known how to do in a long time and just haven't been able to apply in the blockchain setting. Whereas inter-validator sharding, ER, this is more along the lines of what Near or other folks are doing, where I'd put it in the same bucket as L2s, where it's a strategy. With inter-validator sharding versus L2s, anyone can start one. It's sort of up to the community when we're going to have a new island of state. And in intervalidator sharding, it's part of the protocol deciding, like, I'm going to partition the state in this way at this time. So that adds some more regularity, but the same sort of disadvantages you might get from L2s. You have cross-shard latency if you have a transaction that wants to go across multiple shards. You might have to have two-phase commit. You have transactions that can fail more often. So I think I guess we didn't get to talk about reservations with the L2 thesis, but I think, like, if you believe, as Keone was saying, that shared state is where the value of blockchains come from, anytime you start to fragment that state, like, that value proposition erodes a little bit. At least that's my point of view.
Yeah, you were asking about the sort of question of, like, okay, well, if we have 8 cores now, what if we ask for 16? What if we ask for 32? Like, where is the limit? And I think one thing I want to point out is that at the end of the day, the biggest bottleneck for execution is not that CPU time. So it's not the number of cores. It's actually the state access. And so in particular for Monad, Monad is introducing a new database that is built from scratch that's specifically for the problem of storing Ethereum Merkle tree data. And we think that that's really important because in line with all other Monad decisions, it's really preserving full Ethereum compatibility. This is a modular component that just literally makes state access a lot more efficient and unlocks performant parallel execution from delivering much better usage of Merkle tree data stored on the SSD. Now, I know that with other blockchain protocols that don't use the Ethereum Merkle Patricia tree, that's not a specific requirement. But I think in light of the incredible network effects of Ethereum and all of the applications, all the libraries, all of the applied cryptography research, it's all being done in the context of EVM. It's really valuable to preserve that Ethereum Merkle tree data structure. And the way to address the state access problem is through this initiative, MonadDB, that we've been pioneering.
I mean, I've done extensive podcasts with each 3 of you, and I think all of you have communicated the state access problem will be relatively hard and state growth over time. What do you think, Avery, about the state access problem?
State access, I mean, it is a hard problem to solve, but developers have told us very clearly they want shared state access. That's the key thing. They don't want to have this access fragmented across multiple places. Our DeFi projects have told us very clearly that that's where they all want things to be. They want to be composable, and they want to be easy to program with. And so our goal is to make the most parallel, most efficient access, state access as possible. When it comes to the sharding and scaling aspect, we've taken a number of different unique approaches in that space. One thing we've done that I think is pretty novel is actually be able to shard our database across a number of RocksDB instances in a way that allows alleviation of that pressure and allows more access to SSDs. Something we did at our PreviewNet back in December. We ran a replicatable experiment where just did a whole bunch of peer-to-peer transactions and showed we could do 2 billion transactions in a day, which is more than 25,000 transactions a second, which is also more than all credit card networks processing combined. And so we know as we start to parallelize these things, my background is actually in supercomputing. And it's just all about how do you kind of use all the resources available to you as best as possible, whether it's CPU, networking, storage access, and just parallelizing every part of the stack. So having that shared state access being parallelized through the CPUs, the memory, as well as the SSDs, and then thinking about the cross-validator sharding, we kind of hinted at discussing like experiments that run, a validator runs on 1, 2, 5, 10 machines. We're going to see machines with 256 cores going very, very soon. And being able to leverage block STM techniques and all the information for scheduling across all those machines, super, super important. And to drive up performance, keep fees really low, and support the 5 billion users of internet who desperately need this bandwidth.
Any other color on that, or feel good? Cool. I'm curious, just long term, one thing that we've kind of heard is perhaps block space is infinite. There'll always kind of be insatiable demand for block space. Do you guys agree with that? Do you feel like there's going to be a certain point where the systems are kind of good? We perhaps get to gigabytes of throughput per second. The systems are optimized. Do we need 10 gigabytes and then 100 gigabytes in the future? Are there limits to these systems?
Yeah, I think the demands are definitely ever increasing. I don't know about infinite, but I feel like the narrative in the space has changed a lot since, say, 2018 or so, like the era of the gas wars, where I think the feeling back then is like, mainstream adoption is here, but it's just blocked by not having enough block space, and we scale things out a bit, and then like we're here and there's going to be no problem. Whereas today, like, you're at the point where you have several blockchains that are operating way under their capacity all of the time. So Sui is in that category, Aptos is certainly in that category, Solana is in that category. I expect that Monad will be as well after they launch. And then so I think the question is, like, what does the growth look like and where do you start to hit the limits first? My point of view is you won't start to hit the global capacity limits first, which is why we're so focused on local fee markets. If the core value proposition of what you're doing is you create really valuable state and then you add network effects to that state, then I think the inevitable consequence of that is that state is going to become a hotspot. And then the challenge for you is you don't want that to suck up you don't want that to limit your parallelism. You don't want that to add latency to your other transactions. So when we think about like what problems are we going to run into first, we're very, very focused on that. And then for the long term, like this is where the pilotfish story comes in. It's like we think, yes, you want more throughput. There's not some specific magic number that's the max. You want to be able to add more machines when you need more throughput. And you also want to be able to decommission those machines when you don't need it, because you don't want this high operational cost of like running a beefy machine with hundreds and hundreds of cores or tons of memory. You want to do what the two giants do. You have commodity machines, you spin them up when you have demand, and you spin them down afterward. So that's how we're thinking about the problem, but I think folks were wrong in 2018, we could be wrong again now.
Yeah, I want to make 2 points. The first one is, and this is really a topic we haven't covered too much just because we've been so in the weeds about a lot of super interesting technical initiatives, but decentralization. Like decentralization is why we are all here now. And it's clear that there's a sort of like at least like two-dimensional curve of decentralization versus performance. And if one decreases decentralization, for example, by raising hardware requirements, can perhaps get more performance. But at the end of the day, it's really important that anyone be able to run a node, anyone be able to fully verify all transactions and have access to the shared global state. So Logan, to your point about like, are we ever going to stop optimizing? I think the optimization is really around how much performance you can get with a high degree of decentralization, and just kind of going up into the right in that efficient frontier. The second thing, just to point out really, really quickly, is that we care about density of computation within one network. So, there's horizontal scaling. There could be like multiple instances of the Monad blockchain, for example, that are more specialized. And there's vertical scaling with roll-up, or what I like to refer to as the fractal scaling approach. But what matters the most is that for one unit, for one network, like one set of nodes in consensus, we need as much throughput as possible.
I think for us, we think a lot about the costs per transaction as being one of the limiting factors for demand on the blockchain. Having $1 per transaction really limits the use cases in terms of what you want to do. And so I think when it comes to things like payments or financial instruments, seeing that you can do like a payment at 5 thousandths of a cent allows you to kind of take on much more use cases than you could in the traditional world. And so as we start to drive throughput, it can't be just done in isolation. It's got to be done with cost in mind as well. And so kind of keeping pushing the efficiency curve further and further out so that the machine hardware can be used more effectively and be able to drive those costs down for users is something that we think is really important to the adoption. And right now we have, again, 5 billion people using the internet. We have a small, less than 1% of those folks using the Web3 space. And I think cost is a big part of that. And so as we start to drive those costs down, we see more applications building on top of blockchain, leveraging the infrastructure, giving people that utility they're looking for with decentralized infrastructure. And ultimately, hopefully that leads to that mass adoption I think all of us here are looking for.
Fully agree. Maybe as we have 1 minute left, we'll just go do rapid fire questions and we can just go down the line. Are we, I guess, bullish or bearish Ethereum long term?
Ethereum's always going to be around, right? So the metaphor I've used before is like,
Got to do yes or no, Sam.
Okay. Bullish. Sure.
Bullish.
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 Okay. L2s.
Bearish.
Bullish.
Bearish.
App chains.
Bearish.
Bearish.
Mostly bearish.
Cool. Awesome. Well, we'll end it up there. Thank you so much, everybody, for coming and watch. I hope you got to learn a little bit more about these different ecosystems and what they're building.